Hey there, it's Shannon Mathchick-Myers, and today we'll be starting Chapter 13 from the Larson and Edwards calculus text. And Chapter 13 goes into functions of several variables. If you review Chapter 3, if you have time, in your busy day, if you review Chapter 3 in the same text, that will help you with stuff like optimization. This is a lot of the same concepts but covered with functions of several variables. So starting with 13.1, it's just kind of an intro to functions of several variables. So we want to understand the notation, sketch graphs, sketch level curves, and level surfaces if we've got a function of 2 and 3 variables respectively. So for the warm-up, let's find two functions such that the composition h at x is equal to f composed with g at x, and that's equal to sine at x, the quantity squared. So what's the most outside deal going on? Because remember that when you compose f with g, f is that most outside function going on, and g is inside. So our most outside thing going on is beautiful, something being squared. And what is that something being squared? Awesome, sine at x. Beautiful. All right, so a function of two variables. Here's a definition for you. Let D be a set of ordered pairs of real numbers. If to each ordered pair, x and y, in D there corresponds a unique real number, f at x and y, you could think of it as z in equation notation, then f is called a function of x and y. The set D is the domain of f, and the corresponding set of values for f at x and y is the, you got it, the range of f. So, okay, let's just consider something that we've looked at before. Let's think about just f at x is equal to the square root of x, right? What's the domain of this function? I mean, if we were to make a graph here, then what would our graph look like? We'd have, an ordered pair at 0, 0, 1, 1. If we're in the real number system, we're not going to be having any negative values under the radical. We'll have something over at 4, 2, somewhere around there, and at 9, 3, ordered pairs. Okay, there we go. Something like that. It doesn't have a dip, but you kind of get the feel for it. So this here would be just our f at x equal to root x. And then our axis is in the plane, so it would just be x and f at x, or x and y, something like that. And so what is our domain? I mean, we look at our domain. For this one, our domain is just looked at on the single horizontal axis, right? So when you think about the domain, if you were to graph a picture of our domain, right, you would have what? Beautiful. Our domain would be from 0 inclusive, right? So you could do a bracket here. And that would go infinitely to the right. So the domain of f is going to be 0 to infinity. So in set builder notation, what would we have? We would have, for our domain, x such that x is a real number and x is greater than or equal to 0. Cool so far? All right, well now let's take a look at the range, right? The range, if you were, to look at it, let's look at it vertically, right? You don't have to do it vertically, but just for fun, right? We'll have so our range is going starting at 0, right? So I'll do a bracket starting at 0. You could think of it as a closed circle, and then it's going up without bound, right? It doesn't increase really quickly, but it will increase without bound as we go infinitely to the right. So really, we don't have to do this vertically, but that kind of gives us a picture. The output, all possible outputs given a specified domain will be our range, right? So our range in interval notation would go from 0 to infinity, where 0 is included, and in set builder it would be y, such that y belongs to the real numbers and y is greater than or equal to 0. Cool? All right, so now let's look at some functions that are in terms of x and y. Now notice here the domain and the range each were just specified values, so just on a number line, right? Points like or inputs or outputs on a number line, 0, 1/2, 2.9999. Now, when you're thinking about the domain for a function in, 2 variables, like in example 1 here, then this is going to be all possible values of x and y, right? So it will now be a plane, right, of possible ordered pairs that you can input into this function of more than one variable, right? So in 2 variables in this case. Okay, so just some basics. If we're evaluating g, so we have g at x and y is equal to natural log at x plus y, and that's an absolute value. That's sum. So g at 2, 3 would equal to the natural log of absolute 2 plus 3, right? So wherever we had seen an x, we put a 2, and wherever we had seen a y, we put a 3 for this particular evaluation. And so that will give us natural log absolute 5, but 5 is positive, and so we don't need the absolute value. Cool so far? Awesome. All right, so why don't you try B and C just to make sure you're on the right track, and then we'll go on from there. Okay, let's see how you did. So g at e, 0 would be natural log at absolute e plus 0. And that just gives us natural log at e. E is positive. But what is natural log at e? When you evaluate the natural log at the natural exponential function, you just get what's in the power. Well, we have e to the 1, so we're just going to get 1. Cool so far? All right, so next up, g at 0, 1 would be natural log at 0 plus 1 in absolute value. And that just gives us natural log at 1. The power to which we raise e to get 1 is, beautiful, 0. All right, so here we go. Let's go ahead and describe the domain and range. And actually with this one, let's think about the one we just did. It doesn't ask for this, but what do you think the domain would be for this first example? What has to be true of the sum x plus y? Beautiful. X plus y has to be greater than 0, right? It has to be greater than 0 because in general, in your log function, the domain would be from 0 to infinity, non-inclusive, right? So here we go. How could we, how could we write that? Well, let's do set builder notation. Now again, we have ordered pairs, right? So our domain will be ordered pair x comma y such that x and y are real numbers. They belong to the set of real numbers, and good, x plus y, that sum, has to be greater than 0. Awesome. Cool. Okay, so now what about our range? What would have to be true? If that sum, x plus y, has to be greater than 0, what would be true for our output? Well, wouldn't z itself, if all the possible inputs of ordered pairs have a sum that's greater than 0, right? And then when you put those in there, right, what's going to happen to your output? Does anybody remember what the natural log function looks like? Does it have negative outputs? It does have negative outputs, right? Because as you get as you approach 0 from the in the plane, right? If you approach 0 from the right side, you get a vertical asymptote, right, at x equals 0. And so basically our range, therefore, would be some z such that z belongs to the real numbers. Cool? You can see how this is going to go. It's really cool, isn't it? You've got, we can look at some different views. This is more of our traditional view right here. And then as we kind of move it around, you see how it's got that shape of the natural log, and you can kind of see the different views. Pretty cool, huh? So here was the problem we just did, and then we added in the domain and range. And so here's the views that we captured of those graphs. Cool. Awesome. And then now we'll take a look at this guy here. So the ratio y over x is between -1 and 1 inclusive. And then do you remember the range of the inverse cosine? Beautiful. It's going to go from 0 to pi, right? So I don't know, let's put the z from like 0 to 3.5 or -1 to 3.5 to take a look. Pretty groovy, huh? Our graph here. And then we can kind of turn it around. Here's the two views that we took of this one here. And so when we want to describe the domain and range of each of these A and B, for this first one, our domain, remember, will be a set of ordered pairs. Well, the input to an inverse cosine function has to be between -1 and 1 inclusive. And so what does that mean? That means that we would have a couple things going on. The implication here is what? X can't be equal to 0 either, right? Y could be equal to 0, but not X. So we've got a couple of conditions here. So we've got our ordered pair X and Y, right? And such that X and Y are in the set of real numbers. The ratio Y over X is in between -1 and 1 inclusive, and X is non-zero. Cool, cool? All right, so what about our range? So our range, remember that for the arc cosine, the output is between quadrants 1 and 2, right? Inclusive. So what will happen? We will have f of x and y, or you could put z if you wanted, such that the output belongs to the real numbers, right? And what else? It's between, beautiful, between 0 and pi inclusive. All right, so that's the result to the first one. All right, so next up we've got this guy here. Okay, so g of x of y is equal to x times the square root of y. So here, let's just kind of figure this out. What's going to happen for the domain? I mean, isn't it true that x can be any number, right? But what about y? Y has to be greater than or equal to 0, right? So we don't get a negative under the square root. So our domain will be all the ordered pairs x and y such that, beautiful, such that x and y belong to the real numbers and y is greater than or equal to 0. Cool, cool? Now, how is that going to affect our outputs, which will be, you know, given the restriction on the domain, what are all the possible outputs? Awesome. You're going to end up with, well, think about it. Be careful. Y is always going to be positive or 0, correct? But x can take on any value, positive or negative, right? So therefore, the range will be g at x and y such that g at x and y belongs to the real numbers. Cool, cool? Okay, and I'll let you graph that one on your own. Let's take a look at sketching these by hand, right? So here we go. So y can take on any value on its axis, right? So we're gonna basically be worrying about the xz plane, right? G of x and y is like our z. So if we say g of 0 and 0, right? That will just be 0. So we'll have an ordered pair, or ordered triple rather, at the origin. Now let's take a look at g of -4. I'll keep y at 0. And then what would happen to my z value? I'd be at, beautiful, I'd be at -2, because half of -4 is -2. So 1, 2, 3, 4, about here. And then let's take a look at, see, it'd be at about here or so. And then let's see, if we were at g at 4, 0, we'd be at +2 for our z. Be about here. So connecting those, the line there, did that go straight? I think so. You'd have something like this. And then if you shift, right, if you were to say, if you were to copy that line and just shift, so basically do lines that are parallel to that and shift on that y-axis, you'd get your plane. Right? Something like that. Something like this. Right, so you're going to end up with this this planar region. That can vary along that y-axis, right? Cool, cool. And then I graphed it also, so we'd have, you know, some other views of it. Be something like this, depending on your how your view is. So the scale's a little different on this, but you get the general idea, right? So for this one, let's take a look. Why don't we let z equal to 1 just to see what our xy plane will look like. So if z is 1, do you see we'd have 2 is equal to root x squared plus y squared? And then if you square both sides, you'd have 4 is equal to x squared plus y squared. So here, what order pairs might we have? We'd always have 1. I mean, do you see we would have, if x was 2, y would have to be 0, and z is still 1. If x was 0, y would have to be 2 or negative 2, right? And z would be 1. So let's represent the other possibilities. And then we'd have this other one, okay? So this will give us an idea, right? So here we go, 2, 0, 1. Let's let each of these tick marks be equal to a half. So this would be 1, 2. Oops. Okay, so our base, right, would be, you'd have, you'd also have an ordered pair. Wouldn't you also have an ordered pair at 0, 0, 0, right, to get us started? So basically what's going to happen is that you're going to have a series of these circles, right? So you'd end up having, if z is 1, right, up here, you're going to have this cross section of a circle, or so you're going to end up with an elliptic cone, right? Because if you rewrote this, you'd end up having, you'd have z squared, if you squared both sides, would equal to x squared over 2 squared, right? Plus y squared over 2 squared, which is the top half of this elliptic cone. So this is the top half of this, okay? All right, so let's just check it out. So if you had 2, 0, 1, you'd be 2, 0, be about here. Negative 2, 0, 1 would be about there, and then 0, 2, 1 be here, and then 0, negative 2, 1 would be here. So you'd end up with this circular piece here, right? But you'd have, basically it would go like this, right? You'd have these things going, up like this, and you'd end up having your circles that connect them as the cross sections. And so these circles would go something like this. Oh, that went a little wild at the end, but anyway, go something like this, sorry it's so shaky, etc. And then you can shade it in a bit. Shade that. Kind of cool, huh? I know these are hard to draw by hand, but it's kind of cool to figure out what's going on. All right. And here is the much prettier picture of the image. All right, here you go. Okay, so level curves. We can also visualize a function of two variables using a scalar field. This involves assigning a scalar value to z. This is then assigned to the point x, comma, y. So example 4, describe the level curves of the function and then sketch the level curves for the given c values, right? So here we go. If you take a look at some scalar c, right, equal to x over x squared plus y squared, we would get c times x squared plus y squared, just doing a little algebra, is equal to x. And then x squared plus y squared would be x over c, right? So if we wanted to complete the square on that, all right, what would happen? So we'd want to have the x's together. So we'd have x squared and then minus x over c, leave a space, plus y squared is equal to 0. So now, again, completing the square, we'd be adding 1 over 2c, the quantity squared, right? And it would really be adding a negative 1 over 2c squared, which is positive once you square it. And then, so this would end up being, when you square negative 1 over 2c, we'd have 1 over 4c squared. So on the left side here, we would have, let's see, x minus 1 over 2c, the quantity squared, plus y squared, is going to equal to the quantity 1 over 2c squared. Cool so far? All right, so now let's do these pictures. We're going to do these different values of c, so we'll do them in different colors. All right. So for c equal to -1, what would happen? We would have, looking at our graph here, you'd end up with x minus -1/2, right? The quantity squared. And then plus y squared is equal to do you see the negative will go away in the square, right? You'd have -1/2 squared, but that would be the same as 1/2 squared. So you're going to have a circle with radius 1/2 that's centered at -1/2, 0, right? So let me, if we do our scale, whoops. Okay, so here we go. And again, these are, our level curves. So we have, this is x and this is y. And so for our very first one, remember it says a circle centered at -1/2, 0. So -1/2, 0 with a radius of 1/2. Oops. There we go. I like that one better. And then what's going to happen on the other side if you had +1? Good. It's only going to change a little. It's going to change your center. You'd have x minus +1/2, the quantity squared. And then plus y squared is 1/2 squared. And so your center would now be at +1/2, 0. But you'd have a similar circle. Cool. Awesome. All right, so continuing, let's go ahead and do c equal to -1/2. So if we did that, let's see, -1/2, that would make that x minus -1, the quantity squared, plus y squared is equal to -1 squared, which would just be the same as 1 squared. So we have a circle with a center of -1, 0, and then a radius of 1. And so our circle be about here. Pretty good, right? And then what's going to happen? What's going to happen when you go to positive a half? So C equal to positive a half. The only thing that'll change will be the center. So now the center will be at 1, 0. Cool so far? And then continuing, let's see, we did 1 plus or minus 1/2 plus or minus 1. Do you see the trend of the circles? You're going to have, I'm just going to do one side and then I'll do the negative because it'll just be a reflection, right? So let's go ahead and let's do, I don't know. So for C equal to, I'll do positive 3/2. What's going to happen? We'll get x minus, so 3/2, and for C, the 2's would divide out, so you'd have 1/3, I think, right? X minus 1/3 squared plus y squared would equal to 1/3 squared. Right. So 1/3 is going to be out here. About here. And so then so it'll look something like this. And on the other side, something like this. And let's see, that's a little big. That looks something like that. Anyway, you get the idea. And then we've got one more. We've got the 2 here, so we'll do if c is 2, you'd have what? X minus a quarter squared plus y squared is equal to a quarter squared, so that'd be even smaller. So we'll have a quarter is here. Whoops, do the positive side. So a quarter would be here. So a quarter is about here. And then here. Here, here, and here. And then on the other side, we would have that. Pretty cool, huh? So those are the level curves, right? All right, so now you also have where you also have a situation where you could do a level surface, right? So this will be our last example for 13.1. So with a level surface, again, you're gonna, if you let c equal to 0, we're not gonna, it's 3D, so we're not gonna do quite as much here. But if we were to let z equal to 0, or sorry, if we were to let c equal to 0, we're basically letting f of x, y, z equal to 0. Okay, so we'd have 0 equals sine at x minus z. So z is equal to sine at x. Cool so far? So again, that means that the y-axis can vary. And so this is what we would have. We would have, let's figure out our this will give us 2 periods to graph. And then, of course, the output for z will be plus or minus 1. So let's just make we'll make that 1 and negative 1. Cool, cool, cool. All right, so we're graphing this in the xz plane. So when we do so, we will have a sine at 0 is 0, right? Oh, and actually, yeah, the y is going to vary. So sine at 0 is 0. Sine at pi over 2 gives us 1. That'll be about here. And then back down to 0. 3 pi over 2 give us negative 1. Which is be about here. And then 2 pi we'd 0 out. So our graph would look something like on the XZ plane. And then if we just kind of, did this, remember it can vary on our X. So if we just kind of mirrored this, it's going to look something like that. I don't know if I like the lines across. Maybe something like this. Cool? And again, that's letting, our W or whatever f at XYZ equal to 0. And then we get level curves for that. All right, so and it varies across that y axis. You can. All right, so that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe. Bye.